that better? Yeah, all right. Okay, so I'd like to talk about, the program is effective field theories in gravity in particular, but kind of more general than that. And I want to argue that the way we think about them traditionally is that they're Wilsonian actions, and it's kind of a straight-up story that we would have had for any non-normalizable field theory. But I want to argue that that's not wrong, but that there's more. If we're mapping out the domain of validity of low-energy methods in gravity, that's not the only domain. So that it's not sufficient necessarily to be at low energies. And in particular, at late times, there's a generic problem with making predictions in perturbation theory. And you know, I'll get to this, but that's a big question mark if you think that there's weird things happening at late times. So if you think there's an information loss problem for black holes, and your knowledge about black holes is coming from looking at free fields coupled to a black hole background, and you're implicitly in that perturbing in the interactions that could have been there, then a breakdown of predictive power in perturbation theory at late times is a thing to worry about. So the main message is that what's happening in gravity in that case is just like what happens when you have a medium. So if you have particles moving through, say photons moving through glass or something. And so in that sense, there's a well-developed effective description, but it's not the traditional Wilsonian one always. And people have thought a lot about optics, and so there's a lot of tools that are designed to deal with late-time issues, which I'm arguing, when applied to gravity, say sensible things, so we should be using those tools. It's work done with Greg Kaplanek and Marcus Rummel. One of these papers was supposed to have been out, but it's still not out yet, but hopefully this month. So the way I want to tell you the story is I'll do a motivational thing, longer version of what I just told you. I want to then talk about secular growth. So part of the evidence that there's something funny happening at late times comes from cosmology, where there's more symmetries in the problem, so people can actually do the calculations of the perturbative corrections to the leading predictions. And when they do that, they find what's called secular growth. They get something proportional to a small coupling constant, but then that comes proportional to time. So you know that the series you're doing is going to be in trouble for late enough times. And so there's many examples of that now, and I want to kind of take you through those examples. And there's also a story as to how to describe the physics of secular growth, which I want to argue is actually it's a special case of this more general framework. So the party line always starts with Weinberg in this effective field theory story. And the normal way we think about gravity is that it's quantum effects in gravity at low energies is, because it's not normalizable, that we're really, in secret, we're doing a low energy expansion. And it's not just a qualitative statement, it's a quantitative statement. So in the spirit of an effective field theory, you can't just have the Einstein action, you need to include all possible things in your action which involve the fields that you think are there at low energies and obey the symmetries, which typically means the curvature kind of expansion. If you take that kind of an action and you ask, what's the contribution to a graph with E external lines where the external momenta and energies are all of the same order of magnitude I'm calling Q, and it has L loops, and it has V vertices where the V is labeled by N and D. N counts the number of fields that come together at the vertex, and D counts the number of derivatives. Then it turns out that you can track how these various scales in the Lagrangian appear in that amplitude, because the ones that are involved in the interactions, there's a factor, for example, of 1 over m, little m squared, every time I have an interaction that involves, say, curvature cubed. And then the rest of it is dimensional analysis. So the powers of Q are just coming from dimensional analysis. And this expression, tells you what you probably believe anyway. It says that if you want to, the biggest contribution to this expression comes when you make your choices as small as possible. So you make L 0, and you make V 0. Notice in the product over all these interactions, the only ones that are contributing there are the ones with more than 2 derivatives. All the interactions in the Einstein action have 2 derivatives, so they're not included in that last factor. So that just says that the leading contribution is tree-level general relativity, that's why classical gravity is a good approximation to things normally. But this also tells you what the corrections are. The next deleting thing is you either pay the price of having L equal 1, but then you have that last square bracket be take no interactions with more than 2 derivatives, or you work at tree level and take L equals 0, but have exactly one vertex where you have higher derivatives. And what happens there is those compete with each other, and it's the tree level curvature squared interactions that are renormalizing the divergences in the loops, and you kind of carry on like this. And order by order in the small thing, which in this case is the energy of your process divided by the Planck mass, you can predict as well as you like. So that tells you, there's a lot of nice things about that expression. It says that trusting the classical approximation is consistent with working to nonlinear order in the interactions in general relativity, which is what we do. Also, in passing, I notice that the scale appearing in the denominator in front of things like the curvature cube term is not the Planck mass. I didn't write that as the Planck mass. And that's because if you imagine getting an effective action like this by integrating particles out, the scale that would go in the denominator is the particle you integrated out. Typically, there's lots of particles, so you get a sum of terms, each of which goes like 1 over the mass of the particle. But in a denominator, the smallest mass wins, not the biggest mass. In the numerator, like the m Planck squared term, the big mass wins. But if you're working at energies where you've integrated out the electron, it might be the electron mass that appears in that curvature cube term. And so things can be bigger than you might have naively thought. But all right, cosmology is a similar story, and probably I don't need to beat it too hard. The main thing that's new here is that there's zero derivative interactions, which are dangerous at low energies. The low energy scale here I'm calling H rather than Q, because typically it's something like the Hubble scale in cosmology. And you see that when you have zero derivatives, the low energy scale is appearing in the denominator, and that's another way of saying that it's dangerous to have, let's say, a scalar potential with big masses in it. It tends to ruin the low energy approximation. That's one way of slicing the naturalness story in cosmology. But you get away with it often in the real theories that we care about, because that ratio, if the cosmology we're interested in, if the potential we're talking about is dominating the Hubble scale, then h squared would be of the order of v to the 4th divided by m Planck squared. So that particular combination in the box turns out to be 1 for that class of potentials, which are the ones that are of most interest in cosmology. So there's a very nice story. It all hangs together very well. Sorry? Oh, so I took a general potential. Phi is dimensionless the way I've written it, but it's normalized. Kinetic term has a Planck mass in it, and so then v to the 4th is the generic energy in that potential if phi is order 1. So it's just a parameter. It's just a scale. If you have your favorite theory of cosmology, you're going to choose a potential which has a physics scale in it, and that would be v to the 4th. It's just, if you make an inflationary model, you design a potential, and you'll choose the value of the potential to make the Hubble scale whatever you want it to be. And so this is that scale that you had to choose. It would be renormalized. Yeah, everybody gets renormalized, but it's a physical scale in your problem, and it's good to know that it's related to the Hubble scale by the Einstein equations, because that's what saves the low energy approximation. Oh, they're there. In principle, they're there too. They fall into the categories of the d equals 2 term, so they're much like, for the power cutting story, they're much like the Einstein term. So really, the upshot of this is that what counts is the number of derivatives, really, in ordering things, and it's the zero derivative ones that are the problem.
Why don't you have things like f of phi times r squared? Why don't you just get r squared?
In principle, there is f of phi times r squared. The answer I'm giving would apply to that too. I just kind of wrote down some terms just to give you a sense to what's going on. Yeah. The main thing that counts is the number of derivatives. So something like derivative of phi squared times r would be a 4 derivative term, but function of phi times r would be 2 derivative term. And those are the ones that are not punished at high or low energies. So this is any basically. The assumption that goes into this, a formula like this, is that there's only one scale at low energies. And so then that makes this power counting easy, because it's basically dimensional analysis. That I track all the big scales coming from the Lagrangian by counting them from the vertices, and then the rest is on dimensional grounds, whatever the scale is in the problem. So The only assumption that goes into this really is that there's some scale like the Hubble scale, which is small compared to the Planck's size, but it didn't have to be de Sitter space. It could be any small h. What makes it more subtle is if there's more than one low energy scale, then you can't just use dimensional analysis. So you have to do a better job of sorting out where the scales go. And that's why the non-relativistic effective theories are more complicated, because there you've got the mass, and you also have the mass times velocity, which is another scale. So you've got a hierarchy of scales in the low energy theory. And so, but this is the simplest case where you don't have to worry about that. Sorry? Oh, so B, you might be noticing I changed notation on you in that previously I had A. And so A, the difference is A here is an amputated E-point function. And in cosmology, they typically work with unamputated E-point functions. So I'm calling that B, and the power counting is just a little bit different. And so I've given the power counting for correlation functions. So I told you that story because that story is a story that says if you're at low energies, you're golden, basically. You don't have to worry about anything else. But then I told you that there's going to be some question marks about that, one of which is about are examples where people find time dependence appearing when they do perturbation theory. Information loss smells like it's an example where you're looking at very late times and paradoxical conclusions come up. And so it kind of smells like you're pushing the domain of validity of your calculations in a way that would not have been evident from what I told you, because people, for information loss, they choose a whopping big black hole where these quantum corrections are. Big hole means low Hawking temperature, so that puts you in a better and better approximation in this kind of logic that I was describing. So I want to argue now that the domain of validity, it's not sufficient to have a small perturbation parameter. At late times, there's just a generic problem that perturbation theory fails at late times, and it doesn't matter. You needed to have your perturbation expansion be in terms of a small parameter, but that's not sufficient at sufficiently late times to control things. And so I want to kind of set that up in the next few slides. So here, I told you this already. It's the analogy I want you to think about is particles moving through a medium, and the main thing that has that differs from a Wilsonian description like I've been talking about so far is if you have an environment like a medium and it's just sitting there, then it doesn't matter how weakly you interact with it. Very small things can accumulate over time, and that's basically the problem. So let me make that concrete. So supposing you're talking about light, interacting with glass, and it's true. You can choose your material, but it's typically true that any one photon has a small likelihood of interacting with any one atom. So it's a weakly coupled system. You know that if you're ever in a regime where everybody refracts or everybody reflects and nobody goes straight through, perturbation theory was a terrible description of that. Because in perturbation theory, basically nothing happens, and then there's some small change that is the thing that is the perturbation. So that's kind of, and what's happening in this case is that although any one photon had a small chance of hitting any one atom, you go past 50 billion atoms and you hit one, and then you have this coherent interference that gives you refraction and reflection, but only after you've gone that long. So there's a time, the first few atoms it's perturbative, but by the time you get to the geometrical optics regime, you're in this non-perturbative regime. So the good news there, the basic thing that's happening there is that you're looking at evolution e to the I ht. Doesn't matter how small h is, there's a t for which ht is not small. That's kind of all that's really happening. But the good thing is that you also know that we're not helpless in the geometrical optics regime. You didn't have to solve QED exactly to say something about geometrical optics. And the tools that we use for that are the ones that I'm arguing that we should apply to gravitational fields, because gravitational fields are very much like in an environment. If you're in the presence of a black hole, the field is just sitting there, and so you can interact with it very weakly. But what will happen eventually is that small things can accumulate, and there's evidence that they do accumulate until eventually perturbation theory fails. So So now let me, that was kind of the main, that's the roadmap. I want to, in the next few slides, give you the evidence that things, secular growth, perturbation theory gives you powers of time in cosmology. And cosmology is the one where the examples are more worked out because there's more symmetry in that problem, and so it's easier to do the calculations than for black holes. But the logic, I think, is the same. So just remind you about how cosmology works. I'm thinking here about inflationary cosmology, but it doesn't really matter for the argument I'm going to make. Just the story, the way people tell it in cosmology is that if you graph length against time, understanding structure is hard if the scale you're looking at is larger than the Hubble scale. And the yellow line there, when it's angling up, is the Hubble scale at late times, and it's growing in a normal cosmology faster than typical wavelengths, typical physical sizes are. And so the observation people have made is that you've got all these correlations on long distances, and if you trace them back in time, they very quickly go outside the Hubble scale, and then there's no physical way in which you can build in the correlations. And so the way you fix that is you change the extrapolation. And so in an inflationary extrapolation, what happens is that the Hubble scale is time independent during inflation, and then the scale factor is now growing faster than the Hubble scale. And so things that are outside the horizon, or the Hubble scale, in the past, when you go back far enough, are back inside the horizon. And those are the ones, if you look at the inflationary predictions that people like, the ones that, if you kind of ask, is this a good description of primordial fluctuations, the modes that are contributing to the predictions that you like when you compare it to the observations are these ones that are super Hubble modes. So the longest wavelengths in your problem in these kind of cosmologies, and so they should lend themselves to low energy understanding. It sounds like you should be as deep in this low energy regime as you ever need to be. And people in the 80s already knew that it'd be nice not to have to deal with the models. Why can't you just focus on these long wavelength modes and really drill down to their properties in a way which would be less model dependent? And it's only recently, I think, that we realized that the effective theory of these modes, super Hubble modes, has been understood by cosmologists for a while. It doesn't come to us as an effective action. So particle physicists tend to think of low energy theories as being described by some effective action the way I was describing gravity. And that turns out not to be the appropriate description here in the way that you'll see in a second. So here's an example of typical inflationary models. They boil down to some very light scalar field. Here I've taken it to be massless in a near de Sitter background. And you can calculate the endpoint functions for the scalar field, and they behave like that. And A here is the scale factor. And so if you do this in an inflating background where A is exponential in time, then every factor of log A is a power of time, and that's where these powers of time are coming from that I'm alluding to. So in particular, phi squared is linear in time, so it kind of looks like a random walk. What's happening is that you've got all these modes that are they start off inside the Hubble scale, and they stretch until they're outside the Hubble scale, and then once they're outside, they freeze. But depending on the details of the state, there's quantum fluctuations, they freeze at slightly different values in every Hubble patch. And so you end up, if you started with a homogeneous configuration, you end up with a very inhomogeneous configuration because each Hubble scale, the field starts to freeze in a slightly different way because not all Hubble patches will have the same quantum fluctuations. And so the intuition that people get from that is that this statement that phi squared goes linearly in time is just saying that if I look at the range of phis I get at different Hubble patches, that's essentially growing linearly in time. So it's like a random walk. Every patch is kind of walking in a different direction in field space, and the variations just get bigger and bigger and bigger the longer you wait.
How is this related with the usual calculation of perturbation complexity inside the Fourier during inflation?
Yeah, this is that calculation.
So why depends on Ln of A? Should depend just on H. A is something related to geometrical.
Yeah.
Geometry is not propagation variance, so I should expect some results dependent just on H.
Right.
So why?
That's the naive argument. And if you had a massive field, you would have gotten something a function of h, and it would have been h to the fourth divided by m squared. So as the mass goes to 0, that diverges. And what happens is that if you actually calculate this thing, you get an infrared divergence. And that's kind of where the log a is coming from. And it's, so the massless case is kind of a singular limit of the massive case. And it's because of that divergence that you've got another scale that's hidden in your problem that you wouldn't have seen if you made the symmetry argument like that. Not yet, no. So this is just basically, this is a vanilla model like somebody would give you if they have an inflationary story they're trying to tell you. So it's the corrections to this that I want to describe.
It's the same one in here, it's just 5 times R.
No, you could have, so in these models, what people typically do is they go to the Einstein frame. So if you had something like that, you'd redefine it away, and then it becomes a standard thing like this.
So if you were massive, you get some h squared or y squared, not dependent on.
You get h to the fourth over m squared. But time independent, yeah. So the picture is that if you had a really, really small but non-zero mass, and you started off with phi squared, if you took an initial condition of phi squared being some random thing, then it would grow like this linearly until it reached the large value h to the fourth over m squared, and then it freeze there. That's the. So because of the divergence, there was a constant in this that was subtracted, that's not being written there because it was infrared divergent. So when people write these things that are linear in time, they've imagined that somehow they've subtracted that off, and then they're telling you how the thing evolves after that. All right. So now a calculation that was done in around 2005 by Samas and Woodard was, they said, well, let's add an interaction and just say, implicit in the. People like the inflationary story where effectively all they're using is that free prediction of a massless field. But Samas and Woodard said, well, so implicit in that is that the corrections would be small, and so they calculated the corrections. And so this is what turns out to be the leading correction in lambda to the endpoint function. And you see that, this first factor is the one we had before, that it was involving time. But now the thing involving lambda also has a log squared of a, which is also that's the power of time that I was alluding to. So they've done the calculation. It does have this secular growth behavior. But there's actually another thing that they did was they tried to understand what it means. Sorry, just underlining that. So before I tell you what it means, I have to always defend myself. There's two things that people always object to at this point. One is that for single field models, all these issues I'm talking about of infrared divergences and time dependence turn out to be gauge artifacts. So if you're really only exclusively interested in the simplest inflationary models, the things I'm telling you are true, but they drop out of gauge invariant observables. That's the first thing. But if you have more than one field, they don't. So it's one of those things that there's not a general statement that you never get these secular growth. It just happens to be true that for the simplest models, you don't. It's also true that I was raised in a school which said that quantum field theory is like a Middle Eastern religion, right? If you're devout, it will reward you, but if you sin, it will smite you. And infrared divergences are you sinning and being smitten for it. And so the thing you're normally doing is you're asking some unphysical question, and the theory punishes you for that. So there's very little doubt that the infrared divergence part of the story, which is not my main focus, will play out that the infrared divergences cancel in physical answers. But it's still worthwhile tracking it, because if you think about how infrared divergences work in other theories that we know about, like quantum electrodynamics, there's a famous Bloch-Nordsieck calculation between an infrared divergence that happens when photons connect external lines and soft emission of many photons. And what happens there is that those two contributions cancel each other, and they leave you an answer which depends on, say, the electron mass, but also omega, which in this case is the resolution of your photon detectors. So when you sum over the photons that are too soft to be resolved, that's why you get a dependence on omega. The lesson there is that you get large contributions, often large logarithms, and they are not universal in the sense that they depend on things like omega, which is to do with how you actually set up your observable. And so it's useful to see how the cancellation happens, because often, once you've seen it happen, it's capturing for you the biggest part of the finite answer that's left over. All right, so let me go back to this calculation of the secular growth. Samus and Woodard had this calculation where they calculated the endpoint functions for a scalar field to linear order in lambda, and they found that they depended on time. There's a piece of it which depended on time, which is coming from the infrared part of the graph. So there was a party line in the cosmological community as to what's going on, which I'm going to argue was basically right, but you can embed into this more broad framework where you kind of see how to make systematic corrections to what was believed to be true. So what the observation was that the Starobinsky made back in the 80s was, this picture was that phi squared was growing linearly with time. It was like a random walk. And so initially homogeneous configurations were becoming inhomogeneous, but it's not so useful to know the profile of the field you get. It's more useful to know the statistics of the field across many Hubble patches. So we're looking back along our light cone. So here's various slices in the past. Then if you ask how big the Hubble scale is in the past, it's some region like this. So when we look back in the past, we see like a bank of TV sets, which are the field at very many Hubble patches. And so the more useful thing to think about is what's the statistics. These modes that are outside the Hubble scale, they're basically constants in any one Hubble scale. So what Starobinsky proposed was to calculate the probability of finding a particular value for phi as a function of time in any one Hubble patch. And because it looked like a random walk, because phi squared was linear in time, he wrote down a Fokker-Planck equation because he's just trying to describe diffusion. And you choose the coefficients of the Fokker-Planck equation to make the mean and the variance do what they do. So you can calculate what they do in the field theory, and so you design this thing to reproduce the time dependence of the field and its variance. And so the observation that Samus and Woodard made was, if you take that, this is called stochastic inflation. If you take that stochastic inflation story and you use that Fokker-Planck equation to calculate the time dependence of the two-point function or the endpoint function, you get a prediction for what the rate of change of it is. And so they compared that prediction with their explicit calculation, where they got a rate of change because they had powers of time in their perturbation calculation. And they agreed. And so what they found was that the infrared part of an explicit field theory calculation in cosmology is being captured by this Fokker-Planck evolution proposal of Starobinsky's. And kind of what's a little bit unsatisfying there is that it's not really clear how to embed that into the rest of the physics. What's your expansion parameter? What are the corrections to this stochastic picture? And so, but one of the nice things is that if you believe that the Fokker-Planck equation is describing this evolution, it allows you to see what's happening at late times in a way that you can't with the field theory. And perturbation theory is breaking down if you're doing a series in lambda t. But if the evolution is being captured by this Fokker-Planck equation, at late times that just goes to a time-independent probability distribution, which turns out to be this one, e to the minus the potential. So if you had a free particle, then that's a Gaussian distribution. But if you had an interacting particle, like a lambda phi to the fourth interaction, that's a very non-Gaussian distribution. And so in this picture, the statement is that if it's true that the stochastic evolution is capturing these secular growth terms, then they're telling you what's the big thing that's happening. So perturbation theory is failing because small things are accumulating, but they're telling you what accumulated. Each mode as it came across the horizon was Gaussian, but you're ending up with a very non-Gaussian distribution of modes. But there's not a lot of energy in that. If you use that distribution to calculate the stress energy, there's no evidence that the back reaction is destroying de Sitter space, which is often what people would like to have happen. But it does show you that there's a big thing that's happening. It just happens that it's the statistics of the field that's evolving in an important way. So what I want to do now is I want to tell you about the formalism that people use for light moving through glass, and show you that if you apply it to the cosmology, you get, as the leading approximation, you get this Fokker-Planck equation, but you also get corrections to it, which are calculable systematically. And so I want to argue that it's not an accident that this works. It really is that this is kind of a special case of this general late time resummation story that we know about in other areas of physics. So the framework in which people ask questions like this in other areas of physics is in the framework of open systems. And so you've got a Hilbert space, you've got a piece of the Hilbert space you're going to do measurements in, that's what I'm calling A. You've got a piece of the Hilbert space you're not doing measurements in, that's what I'm calling B. It happens that if you know the reduced density matrix, the trace of the full density matrix over B, that's sufficient. If you know what that is as a function of time, you can predict the time evolution of any observable in the sector A. So that's a complete solution of your problem. And in principle, what you want to do is take the Liouville equation for the full density matrix, take its trace, and then figure out from that what the reduced system is doing. So this is very much like an effective field theory in the sense that you're choosing to look at some subset of the system. But the difference is that in an effective field theory, you're normally using, say, energy as the criterion for what you choose to look at and what you choose not to look at. And because energy is conserved, you're guaranteed that the evolution in the low energy sector will be unitary. So there will be some Hamiltonian that describes it. It's just a question of what the Hamiltonian is. Here, there's nothing that says that you're just choosing not to look at things, and then there's no conservation law forbidding you from exchanging information with B or entangling with B. And so in general, when you have a system like this, what could happen is you could thermalize, or it could be that you decohere. And so that's typically not described by Hamiltonian evolution because a pure state is becoming a mixed state. And so this kind of a system in general won't be described by a Hamiltonian. And so although there will be an effective description, I will argue, it's not naturally cast in terms of a Hamiltonian or effective action. And that's kind of why particle physicists, we tend to be blind to it. So the general logic of it is you take the trace of the Liouville equation, and then in general it's a mess, because it's just complicated things can happen. But it's the effective field theory part of it, or the effective part of it, is that if you look at late times, if the system that you're not looking at, sector B here, has a correlation time, so say it's a thermal bath or something, so there's a typical time scale associated with its collisions. If you ask questions that are on time frames long compared to that, things can simplify. And what happens often is that the simplification happens because if you take the trace of the Liouville equation, the right-hand side can be written in terms of just the things you're trying to solve, so some known correlation functions and the reduced density matrix. And when that's true, it's possible to to reliably figure out how observables behave at late times, using an argument I'm about to give you. So if you think about how you make late time predictions, the simplest example that you're all familiar with is the exponential decay law, right? If you have a bunch of atoms that are decaying radioactively, we know that the survival probability goes like an exponential of minus gamma t. Gamma is typically some coming from some interaction. So you normally calculate gamma in perturbation theory. So say it's order g squared, where g is some small coupling. What you really calculate when you do those calculations of gamma is you calculate the survival probability, and you find that it goes linearly in time. And that's, we interpret that as being, that was the leading part of the exponential. But in principle, you could have argued, well, how do you know it's an exponential? If you wait for times long compared to the decay time, why do you trust the statement it's an exponential, given that something involving gamma squared is arising at order coupling constant to the fourth, and you didn't really do calculations at that accuracy? And of course, there's an argument. The argument is a renormalization group kind of an argument. And the way the argument works is you argue that that the rate of change of the survival probability is proportional to the number of undecayed atoms, and the rate is something which is it's just basically a Poisson process where no one decay cares about the other decays, and that gives you this differential equation: dn dt is minus gamma n, and that's the thing that justifies the exponential decay. But once you know that's true, then you can calculate what gamma is by working to linear order in t. But you really believed that there was a exponential decay because you had the differential statement about dn dt had a broader domain of validity than did the expression for n of t itself. And in the renormalization group language, what you're doing here is you're resumming all orders in g squared t, but you're dropping terms that are g to the fourth t, for example. You're dropping things that are down by extra coupling constants but not enhanced by powers of time. And basically, this is the argument, as far as I can tell, that is always the argument that people use in any area of physics when they want to make late-time predictions. And it's like a renormalization group argument, because in a renormalization group, you calculate the change in a coupling constant alpha. It involves some logarithm of scales. You differentiate that to get something involving the rate of change, involving the beta function, and you integrate that again, and you trust the answer when you've integrated again, not to all orders in alpha times a log. And it's because the differential version of the evolution is got a broader domain of validity. And so the goal is always to try and set up the evolution of what you're trying to follow in a way where you have an evolution equation which does not make explicit reference to time. It just involves variables like n. And so although when you derive the rate of change of n is proportional to n, you do it on you do it in some small time window. That's what these pink things are supposed to be. There's time windows. But since it doesn't matter where you started in this rate equation, the validity of the differential evolution is really the union of all those time windows. And so you can trust, when you integrate that equation, dn dt is minus gamma n to get the exponential, you can trust that actually over much longer times than the times that you use to calculate gamma when you're doing perturbation theory. So that's a case where, although perturbation theory was failing at late times, you can fix it because of the arguments like this. So I want to show you how that, in the case of cosmology, turns into the stochastic story. So what we do for cosmology is we have to have system A and system B. So system A is the super Hubble modes. Those are the ones that we want to see what they do in cosmology, because those are the interesting ones. System B is all the modes whose wavelength is Hubble scale or less, say. And then now what we do is we take the trace. There's a Liouville equation that tells you how these fields, these modes evolve, and they interact with each other. And if you work your way, if you kind of start in the Liouville equation, the thing that's linear in the interaction is simple, because that's always describing a mean field evolution, it turns out. And it happens that if you, for cosmology, focus on how modes evolve, how long wavelength modes evolve, the whole stochastic story is in this first term. So that basically you didn't need to know about interactions to see how stochastic inflation works. So what happens is, the statement is that if you have a free field basically on let's say de Sitter space or some cosmological background, it's a free field so that there's a Schrodinger equation for its vacuum, if you like, the Bunch-Davies vacuum, which you can use to calculate the evolution of anything. But in particular, you can calculate the probability of finding a value for phi, which in this language of the density matrix would be the diagonal element in the density matrix for phi. And because it's super Hubble modes, they're basically constants on any one Hubble patch. And so the basic assertion is that if you're in an inflationary slow roll situation, the evolution of the Schrodinger evolution of the ground state of the field theory is being well described by a Fokker-Planck equation, which is not in general true. So it's not in general true that if you take the quantum evolution of something, you can describe that using a classical evolution. And the thing that's the obstruction is normally if you calculate the expectation value of x and p and x, classically those will be the same. So the difference will be 0, whereas quantum mechanically these things will fail to commute and you'll get something order 1. And it's because of that, it's not in general true that a Fokker-Planck equation captures a quantum system. But if you're in the WKB limit, where your wave function has the form of e to the I, some big parameter s of phi, or s of x if you like, then your momenta, minus I d psi dx, is just going to be given by lambda ds dx times psi. So in the WKB limit, when lambda is very large, your momentum eigenvalue is effectively a function of your position eigenvalue, so it's effectively classical. And the statement is that something like this is happening at order 1, not at order lambda, so it's suppressed by order 1 over lambda. So if you're in the WKB limit, it can be true that Schrodinger evolution is being described by stochastic evolution, and it happens that if you look at fields in de Sitter space, once the mode leaves the Hubble scale, they become more and more WKB-like. They become what they call squeezed. That you wait a couple Hubble times, once the mode crosses that's another way of saying what it means to freeze. So the mode crosses the Hubble scale, And then freezing means that effectively the momentum of the mode gets nailed down because it's not moving. And it gets nailed down in exactly this WKB sense. And so you can kind of see that if you focus on the rate of change of the diagonal part of the density matrix, you can do diagonal or off diagonal for the quantum system, that it's plausible that there will be a Fokker-Planck evolution, and there is, but you can also calculate the corrections to it because you know that you're looking at a WKB approximation. And so that goes through very well. And so people they rediscover this thing every 5 years. That shows you that people are not completely happy with the derivation of the stochastic inflation, the fact that they rederive it every 5 years. But the bottom line, though, is that the stochastic story is the leading piece in this general open system story. But there's more. If you go beyond leading order, there's a second order, there's two terms. L here is just something involving the traces of the interaction Hamiltonian. And this is the thing that starts this is the first time you get something which does not look like Hamiltonian evolution, because it's not the commutator of some Hamiltonian with rho for some choice of the Hamiltonian. And so in particular, this is where if you looked at the off-diagonal parts of the density matrix, you would see how they evolve. And then what happens in cosmology is the off-diagonal parts of the density matrix very quickly go to zero, it turns out. And so that's the explanation as to why quantum fluctuations during inflation are turning into classical fluctuations in the later universe when we actually look at them. Part of that decoherent story normally involves the density matrix is diagonal, but what basis is it diagonal in? Because it'll make a difference if you have a classical distribution in field space as opposed to canonical momentum space or something like that. And this says that this predicts that what should happen is, because of this WKB story, when a mode crosses the Hubble scale, its canonical momenta are becoming functions of the field itself. It's always true. One thing I should say is that in this decoherent story, what happens is that the density matrix becomes diagonal in the basis that diagonalizes the interactions between sector A and sector B. That's the general statement. And I'm making an argument now that is always the field basis, that because modes are in this WKB limit where their momenta is the same as the field, if you take the interaction Hamiltonian, it's basically a function of the field. And so that means that it's always diagonalized in a field basis. And that's the explanation as to why at late times it's a classical distribution of fields, which is the thing that you should expect to get. And that's what people in practice use when they're doing late time cosmology. When they take the primordial fluctuations, they take a classical distribution in field space. And this is arguing that cosmologists would argue that you don't need to understand decoherence, because they would say if you're calculating correlation functions of fields, and you write that as some integral d phi of phi times a density matrix, phi rho phi, they would say that if you're only ever looking at correlation functions of fields, you only need the diagonal parts of the density matrix, so it doesn't matter what the off-diagonal terms are doing, and that's not false. But this is saying that you do have more information, that although if you ask these questions, you don't need to know what the off-diagonal terms are doing. Cosmologists call this decoherence without decoherence, because they're saying that you don't need to know the off-diagonal terms because you're always calculating the same thing. But this is arguing that you have more information. That's not only that these calculations don't depend on the off-diagonal terms. The off-diagonal terms are going to zero. And so that means that if you're looking for quantum observables at late times after 60 E-foldings, you're going to fail, because the things are decohering. It really is true that you're going to a very classical state on a time frame of several Hubble times during inflation. Okay. All right, so that's kind of a long story short. There's evidence of secular evolution in cosmology. There's evidence that it's described by stochastic inflation. And there's evidence now that that description is a special case of this general open system story, where you choose as the system you're going to look at the long wavelength modes, the super Hubble modes, and you choose the system you're not looking at as the short wavelength modes. And right. There's a subclass of theories for which you could do this, but it's all pure gauge, so it doesn't matter. And in that subclass, there's really nothing to answer. But the broader class question that's the exceptional class, is what I'm arguing, is that in the black hole case and in general cosmologies, the generic thing is that you do have a problem. And I would say that the Matthias and company, they kind of oversold. It's true that the ones that you most care about when you're comparing the data are the ones for which it doesn't matter. But that's not the same thing as saying that there's not an issue. All right, so now I want to close out quickly with I want to talk about qubits in moving in various curves in space-time, not because they're interesting, but because I've been alluding to this formalism like it's some sort of a mysterious thing, and it's actually, I want to do this example just because it's really concrete. You can see exactly every step along the way at what point it becomes possible to predict the late-time behavior, and what are the assumptions that go into that. So what I want to do is I want to take a two-level system, a qubit, couple it to a field, and so it'll couple to the value of a field along some trajectory, which will be the trajectory of the qubit. And we've done this for various examples, but it doesn't really matter. And what will happen is that I want to think of the qubit as sector A, and I'm going to think of the field as sector B, and we'll just ask, how does the sector A evolve? And in particular, I want to get at the late-time behaviors. This is like an Unruh detector. And there's a classic calculation of this, which it turns out is it's not wrong, but it doesn't give you late-time behavior in a way that you'll see. But you can get the late-time behavior. So let's take so here's our qubit. It's omega is just the energy between the two levels. And I can imagine there's an interaction which causes transitions between the two levels when you couple to the field. G is a coupling constant. And I'll take some field. Mostly I'll take a free field, but sometimes I'll be interested in keeping the interactions of the field. So the interaction I'm going to be perturbing in mostly is that one. But sometimes, probably I won't get to it this time, but there's a story also about what happens if you want to. There's a secular growth effects thing that happens here, which is tangential to what I want to say, the main thing. All right, so now what do we do? We just take the Liouville equation and we integrate it. And so in perturbation theory, it gives you the standard formula. So it's nested commutators of the density matrix with the interactions. And on the right-hand side, you're getting the only place, the density matrix is always the density matrix at the initial time, because that's what it meant to integrate the Liouville equation. I'm working in the interaction picture, so that's why the interactions are functions of time. And I'm imagining that at the initial time, the system is in an uncorrelated state. So the field is in its vacuum, the qubit is in some sort of state. Normally, I'll take it to be the ground state, but they weren't correlated with each other. So now what we do is so if I just take that qubit story, plug it into that top line, and you get this bottom line. So it involves correlation functions of the field in the vacuum because of the choice I made of the initial state. So those are the Whiteman functions for the field. And so you evaluate the Whiteman function along trajectory of the qubit, then this is giving you a formula for how the density matrix of the qubit evolves into time, which should have this late time problem, and it does have this late time problem. So if you look at small times, this is a kind of a classic calculation that Sciama and Candelas did back in the early 80s, I think it was. You can calculate the rate with which the ground state there's transitions to the excited state due to the interaction with the field, and that gives you this famous answer that Sciama and Candelas got, which is it has a lot of thermal features in it, but basically it's given by the Fourier transform of the Whiteman function, and that tells you the rate for doing these transitions. And zero is just in it. Yeah, I prepared that state in an uncorrelated way at 0. And so then I'm asking what happens after that. So the thing that was special was I demanded there were no correlations at that point. All right, so this is what I'm about to argue is that this rate that they calculated is accurate. As you turn on the interaction with the field, it's the rate with which you start to occupy the excited level. But it's not the late time rate because unlike for decays, you can't forever populate the excited state. Unitarity stops you. You have to know about the fact that there'll be a feedback, which will not give you an exponential time dependence here. And the goal is to identify the late time behavior. And the late time behavior is going to turn out to be, at late times, it approaches a thermal state in the example we're going to look at. And the approach is got some exponential with some rate, but the rate is not that rate. It's a different rate. So you can calculate both this and that. So the way that you calculate, this is the main argument. This is how people in other areas of physics calculate the evolution of these open systems. And the basic problem with that Liouville equation that I showed you was that the left-hand side is the rate of change of the reduced density matrix, but the right-hand side doesn't just refer to the reduced density matrix. It refers to the initial condition for the full density matrix. So you don't have an equation for the variable you're trying to find. But that's a problem you can solve once and for all, and that's what Nakajima and Zwanzig did in the 60s or something. Because basically it's a linear problem. The evolution, the Liouville equation is a linear process in the space of operators in the Hilbert space. And the projection onto the reduced density matrix is also linear. And so what you can do is you can just take the Liouville evolution and project it onto the subspace that you're trying to follow for sector A. And that gives you this. So P is defined up there as an operation where I take the trace over the sector I'm not looking at, in this case the field, and I take the ground state in that sector. That is a projection operator. If I square it, I get it back itself. And so 1 minus it is also a projection operator. So what I can do is I can take the Liouville equation and I can just, put in, insert factors of 1 equals P plus Q everywhere. And what that does is it shows me, so P is the thing that is the sector I'm following, Q is the sector I'm not following. It gives me coupled equations which tell me how the thing I'm not following is evolving as a function of how the thing I'm following is evolving. And the logic is you take the bottom equation here for the thing you're not following, solve it, and plug it back into the first equation, and you can write an equation which is just talking about the variable you're trying to track. And it'll be an integral differential equation because you did this integral, but it's got all the information of the full theory, but it's explicitly written in terms of the variable you're trying to follow. So it's not yet simple, but it's useful in the sense that you can set up approximations for how to solve it at late times. So I do what I told you in the last slide. In perturbation theory, you get this is this first order thing, and you see that it involves the curly row here is the reduced density matrix, and the right-hand side only involves curly row as a function of s, not at the initial time. And that's because I've solved for the sector that I wasn't following in terms of the sector I'm following. And so what makes this thing complicated to solve is that it involves an integral over the history of the evolution of the interaction between the environment and the particle, the thing you're following. And that's the right answer. In general, things are complicated. In general, things are not Markovian. Things depend on the history of how you how things evolve depends on the history of how you got there. But at late times, the essence of what will allow us to make late time statements is, it's often true that these integrals are sharply peaked in time, and that's the statement that there's some characteristic correlation time for the environment that you're looking at. And if you're looking at times later, if you're interested in times later than that, then you can Taylor expand. If rho is varying more slowly than the correlation functions are, you can Taylor expand rho in powers of s minus t, and when you do that, rho will come out of the integral, and then you get a very Markovian limit, and that's the one where this argument I gave you about integrating and trusting a solution at later times works. That doesn't work here because you've got a convolution in time, and so you can't make this argument that all times are equal because you really have an integral over the history of how you've been interacting. So take that cubic story I gave you and I do all the words I told you, and this is what you get. And so here we still have a correlation, which is a convolution. So rho 1, 1 and rho 1, 2 are the top left and the off-diagonal pieces of the density matrix. You see that they decouple from one another, that rho 1, 1 doesn't care about rho 1, 2 and vice versa. There's an integral over the history, and then the simplicity happens when you imagine that the correlation functions are peaked. And so typically what will happen in the examples I'm going to look at is that correlation functions are thermal, and so the thermal scale sets the scale of the peak. And so when that's true, these correlation functions are basically delta functions on the scale over which rho is evolving. And when that happens, the integrals go away, and they give you a differential equation that you can solve for late times. So there's also one other thing you have to worry about, but it's not so important. So this is what you get. You get this is called the Lindblad equation. So that equation, which was a non-local in time statement, is called the Nakajima-Zwanzig equation, and that actually captures the same physics as the full system did. So it's just as complicated to solve as the full system was. But at late times, when you're looking at times long compared to the correlation time of the environment that you're ignoring, then things simplify because the integrals don't involve the thing you're trying to solve for. And so the variable you're solving, in this case, rho 1, and rho 1, you've got some Markov process where the rate of change of rho just depends on rho, and it doesn't depend on the whole past history of rho. And so this is what it turns into. And this is the kind of equation that I can make that argument where I can integrate the solution and look at it for later times. The Candelas-Sciama piece is that first term, and that's kind of makes sense because if you really were ruthless in expanding in powers of g, then rho 1 and rho 1 were 0 at the initial time, and so their difference from 0 is also of order g, and so those you'd throw away all these other things if you're really being completely anal about expanding in powers of g. But the lesson of the late time perturbation theory is that perturbation theory is not enough, that you need to include these other terms because that's what gives you the information to resum late times. It happens that in the examples that I'm going to look at, because they're thermal, at late times that the state goes to a thermal state, because in all the examples I'm going to look at, there's a what's called a KMS condition. And because it's going to a thermal state, you can kind of watch it approach the thermal state. And there's two scales because rho 1 and rho 1 evolve independent of one another. So I'm going to call those the thermalization time and the decoherence time, although strictly speaking, those two times really involve both of these times. So there's two time scales that are slightly different from each other, which control the approach to equilibrium. And that just means that the off-diagonal terms are going to 0 at a rate which is slightly different from the way the diagonal terms are adjusting to have the thermal ratio. And then there's also a frequency renormalization, which doesn't really matter. All right. So, for example, if we did this for de Sitter space, so if we just had a qubit sitting in de Sitter space interacting with a field in de Sitter space, the Whiteman function you can calculate, and it's that expression up there. Capital M is the thing. So now I'm imagining I've got a scalar field that's coupled to the curvature in a non-minimal way. So C is the non-minimal coupling to the curvature. M is its mass. Capital M is the sum of the mass in the non-minimal piece. In the special case that it was a conformal scalar, nu would have been a half, and so everything simplifies down to some analytic function. That shows you, the analytic one, shows you what's generically true, that these correlation functions are peaked. And so that sine h has an exponential fall-off, whose fall-off is set by the Hubble time. If you do this in Rindler space, it's set by the acceleration time. So it's the usual thing. And so what happens is that in this case, the qubit thermalizes to the de Sitter temperature, and it does it on a time scale which is set by the coupling squared times the Hubble scale. Unless the mass is very small. In de Sitter space, what happens is that there's a phenomenon of critical slowing down that happens, that if you get very close to zero mass, it's always true that at late times you have this Markovian evolution, but it might be that when the mass is small, you have to wait for a time scale of order h squared over m rather than order 1 over h. But eventually, at late enough times, you always get to this Markovian limit. So that just gives you an expression for what the times are. So let me conclude. So the bottom line of that example was that there's a very well developed framework for describing open systems where you're tracking one variable and not tracking the other variables. And you're not doing that based on conservation law. So it's, in general, different from a Wilsonian effective field theory. And it's adapted to these situations where you have particles moving through a medium. If you have an electron, you shoot an electron through a medium, and an electron comes out, it might not be the same electron. It's you don't in general know. In general, what happens when you have a medium is that you can exchange information, you can exchange entanglement with that medium. And then that's what makes in general, the evolution complicated. But at late times, it's very generic that things become Markovian, and you can describe the late time evolution in a reliable way in perturbation theory because of that. And so the issue becomes, do you have a hierarchy of scales in your problem between the correlation time of the environment you're not looking at and the time scales of interest to you? If you do, then you can normally profit from that and make reliable late time predictions. And when you apply this to cosmology, it includes but extends the Starobinsky stochastic story. There's a story for black holes that I haven't talked about. There's fewer explicit calculations for black holes, so there's less evidence for there being secular growth in that case. But we have a calculation which is kind of partway done where it looks like it is true in general that the black hole also has a secular growth, and it kind of has to, because anything that's thermal has to behave like a thermal system, and thermal systems have secular growth. If you're in a thermal bath, then small effects where you interact with the bath grow over time, and that's kind of a characteristic feature of thermal systems. And so it would be a surprise if black holes didn't have secular growth, because they would then not be thermal if that were true. But the evidence is that they do have the secular growth. You know, the natural question is this story going to change the information loss story? And I suspect not. I suspect that what seems to happen is that the correlation functions, you know, the basic firewall kind of story says that if you have particles that are being radiated from the black hole and the particles fall in and they're entangled, if you want to get the information out, you have to entangle the one coming out with one coming out at a later time. And then there's these general, you know, monogamy theorems that say you can't entangle two different things with each other. And what's kind of unsatisfying with those arguments is that they're very implicit. I'd like to actually watch the entanglement go away. And I think what's happening in these things is that the entanglement normally goes away like 1 over time squared. And what's happening when you do this late time, the secular growth is making that fall off more slow than 1 over t squared, but it still falls off. So I'm thinking, so if I kind of had to bet money now, what looks like happens is that there are changes at late times in the predictions for black holes, but they probably don't change the basic information loss problem that people are grappling with. So thank you for your time.
So I have a question about going back to cosmology.
Yeah.
Correlation functions. So the 3-point correlation function, which measures non-Gaussianity.
Yeah.
Do you have any results that are different from the usual Malacena result or single field inflation or non-Gaussianity? Is this
No, I think that there will be results. There's two things, because if you looked at the 3-point function, for example, if you want to really get the non-Gaussianity, then there will be corrections to it, and they'll have the secular growth thing going on. But if it's a single field model, which is what Malacena was working with, then you always fight this thing that it's mostly it's a pure gauge artifact. So
so for multiple fields you would have?
in principle, yeah, the multiple field has them, and they've seen them. It's just there's very few models where when people have multiple scalar field models, when they get to the point where they see these problems, they usually don't get to that point because normally they're just working at the level of free theories. But what the cosmologists often do is at that point, if they do see that there's a problem, they'll just kind of stick in they'll just choose a time. You know, they'll say, well, I'm interested in it. So they're not really thinking about it very systematically, I don't think.
But then you can set for these multi-fields what is the maximum number of equals inflation, no, that can happen inflation before everything breaks down. So, for example, there's some people that like the term inflation or a number of equals that is gigantic. And your argument says that if inflation had happened forever, you're getting out of control because of the secular effects.
Right. The first approximation, I don't trust anybody who talks about eternal inflation, because that doesn't mean that they're wrong. It's just that I think. What's that?
You're getting on camera, so.
Well, I think it's fair to say that people haven't. Some people have, but it's true that that these issues haven't percolated in the community very well yet. So I think that people say many things about late time inflation that and they probably rightly, but don't trust them until I see how it works myself. And so it could very well be like the black hole story, that the black hole story, I think it's going to be the same story people tell. There's a complication to it that if you follow these issues through, if you want to really do a reliable calculation, you need to include these corrections, but it might not change the conclusion at the end. So it could very well be true that internal inflation has that same look to it. So beyond that, you really need to know exactly which claims. So.
Could this open EFT approach be done also for the super Hubble modes as compared with the
Yeah.
super Hubble modes?
Yeah, and that's that.
It shows the qubit example, right?
Yeah, but it's true. It's also true that if you take a field, if you take the super Hubble modes of a field, and take that as sector A, and take the sub-Hubble modes as being sector B, and not for the qubit but for the whole field, that actually gives you the stochastic. Yeah.
And then the corrections would get the same thing as with normal usual perturbation theory, but in the non-linear regime, because in the linear regime the modes does not interact with each other, right?
Right.
So there exists this check of validity between this calculation from open EFT and this peer-to-peer calculation, or is the same?
So I think it's, in principle there's a check, but in practice the stochastic calculations. In practice, in that stochastic story, there's coefficients in that Fokker-Planck equation, which are functions of all the parameters in your problem, the mass and the slow roll parameters, and what they in practice do is they choose they'll give you the noise. They quote the noise, which is the one that's appropriate for a massless particle in de Sitter space, and so. They basically, I think it's because it's hard for them to calculate how these things depend on these various parameters. In practice, it's difficult to compare because the calculations don't exist. So we've done a calculation where we have calculated the mass dependence and the slow roll dependence of the drift and the noise, say, but that hadn't been done before. So it's not like there's a second calculation you can compare it to. A nice thing happens that if you do these corrections, what happens is that one of the things that's weird is that the rate of change of the variance of the field is an infrared divergent thing, and so it's tempting to think that the things in the Fokker-Planck equation are going to be infrared divergent too, and that turns out not to happen because of these corrections. The corrections are exactly what they have to be to make the noise and the drift infrared safe, and that has the right kind of smell to it, because what's probably going to happen is that at late times all your observables will be describable in terms of the coefficients in the Fokker-Planck equation, like that probability was e to the minus v, right? The thing in the Fokker-Planck equation will be the thing that controls the late time behavior. And so the very least you'd want for infrared safety is that those things be infrared finite, like the noise and the drift. And in the examples that we've looked at, when you put the corrections in, it looks like they are going to diverge, but then they don't, because the corrections are exactly what they had to be finite. Well, it depends on the interaction. So, for example, in this qubit case, here the characteristic timescale in the bath is h inverse. So late would be, you have to be much longer than h inverse, and the timescale that we got when we did this turned out to be set. Those C's are timescales, and so you can kind of see that because they go like 1 over the coupling. So say omega was really small, in which case these become just basically 1 over g squared to h. So as long as g is small, which it has to be for perturbation theory, the time scale you're being led to here is naturally very, very long compared to the Hubble time. And so the thing, it likes to work that way. It likes to get, if you're doing it in perturbation theory, the interaction is the thing that's making the response slow. And so it's putting you in a regime. I think that's why generically, it's generically true that this late time regime works, because if you're doing it perturbatively, the couplings are by construction small, and so the relaxation is very, very long compared to the scales in the bath.
The model you have for inflation and the effective field theory you have, do you know what these genes are, or is it on the model? Or?
Oh, in that case, So in that case, if it was lambda phi to the fourth, it would have been, it's typically the Hubble scale, yeah. So in all the inflationary models, it's the Hubble scale is playing that role because basically it's behaving like a thermal system, and so the temperature is the Hubble scale. And the exception to that is if the mass is really small, because in that case, then there's this critical slowing down thing that happens where you still fall off of the time, but the time scale for small masses turns out to be h squared over m rather than 1 over h. But you eventually get to this late time limit. It just takes longer. But unless you have if you don't dial the mass to be small, then it's generically the Hubble scale. In the black hole case, if you kind of say, more or less the argument is that if you're saying that the energy times time is order 1, you tell me the energy and then I'll figure out the time that I need. And so if you're in the black hole case, if you kind of say, supposing I have a Planck suppressed interaction, then if you ask what time would I expect that to be breaking down, it's kind of the page time basically, because it's the time that you would build out of the Planck mass and the mass of the black hole.
It's not when the black hole gets small.
It's kind of the page time would be when you're kind of losing an appreciable order 1 amount of information. And that's something which is, I can't remember the power of m over m Planck. But that's kind of typical time. If you just estimated when you'd expect perturbation theory to fail, given that you had a Planck mass suppressed interaction, you get something of the order of the page time. So it's kind of, you're exactly in the place where you'd be suspicious about late times, in principle.